Hello, guys and gals, and welcome to the video on 5.2D. So in the last video, we talked about what reaction orders are, and we discussed the differences between them. In this video, we're finally going to talk about how we find reaction orders. Now, this section is pretty long, so I might have to break it up into two videos. We will see. Let's just get going, okay? So now that we know what reaction orders are, we can finally figure out how to solve for them. In complex reactions, we have to have experimental data to determine the order for each individual reactant. Unless we're specifically told that a reaction is elementary, we're going to always assume that the reactions we're working with are complex, okay? So we already know the orders for the reaction between nitrogen monoxide and oxygen gas. So let's use that as our first example for how to solve for reaction orders. So in order to solve for the reaction order, I had to be given data that looked like this, okay? Notice that this is concentration and rate data. So this is a big hint to me that I'm going to be working with the regular rate law, what we've been working with the whole time in 5.2, okay? Experimental data like this has to be given to us, or some other form of experimental data that we can use to understand this has to be given to us. Basically, we can't come up with this. We've got to be given data like this. Let's break down what the table is telling us before we figure out how to use it, because the fact is, if you can't read tables and graphs, you're going to have a really hard time on the AP exam, okay? So let's make sure we understand what the table is telling us. First, the first column is just saying that we've done 4 trials of the same reaction. I know they use the word experiment, but this is the same reaction we're talking about. So you can replace that word if it messes with you with the word trials. We've done 4 trials of this experiment. The next column tells us the concentration of nitrogen monoxide. Remember, those brackets mean concentration of whatever's inside. This is going to tell us that it's in molarity, which is moles over liters, okay? And this little subscript 0 here that's next to the bracket is telling us that this is the initial concentration. So we are looking basically at time equal to 0, the split second that the reaction occurs, okay? We're looking at the initial rate of the reaction when it's going the fastest. That's what we're usually going to compare when we're looking at reaction orders, okay? We're always going to compare the concentration initially to the initial rate, because that's the point where the reaction is going the fastest. So it's going to give us some pretty accurate data if we start there. This third column here is telling us the same pieces of information about oxygen instead of nitrogen monoxide. So the initial concentration of oxygen. This final column is telling us the initial rates of each of these trials. And that unit is molarity per second. We're going to want to pay special attention to that unit, because if we need to work with units later on, we need to know that we were working with seconds. We can always assume that we're working with molarity unless told otherwise, but the time is going to be different. So in this case, we know it's molarity per second. Now that we know what this is, or what each of these columns is telling us, we can look at how we use this information to solve for the order of a reaction. So I put the data down here again so that we could read all of that and then see it again. In order to find the order of an individual reactant, we need to see how changing the concentration of that reactant only is going to affect our rate, because that's what the order tells us. Remember, the order of a reaction is a shorthanded way to tell us, if you change the concentration of this reactant, here's how your rate is going to be affected. So we need to find 2 trials anywhere in this data where the concentration of nitrogen monoxide is changed, but the concentration of oxygen gas is not. Now that's very important, because we need the concentration of oxygen to be constant. Otherwise, we will have no idea what changed our order, or what changed our rate, okay? And if we can't determine which reactant affected the rate, we can't determine the order of a reaction. So I'm going to look for 2 trials where nitrogen monoxide concentration has changed? Well, between trials 1 and 2, the concentration stayed the same, so I'm not going to look at that. Between trials 1 and 3, the concentration of nitrogen monoxide doubled. Well, it also doubled between trials 2 and 3, right? But the problem is that between trials 2 and 3, oxygen's concentration changed as well. So I cannot use trials 2 and 3 to help me figure out the order for nitrogen monoxide. But if I look between trials 1 and 3, nitrogen monoxide's concentration has doubled, while oxygen's concentration has stayed the same. So that means if the rate of the reaction has changed between trials 1 and 3, only nitrogen monoxide is to blame. So we can determine the order, there we go, of nitrogen monoxide if we can determine how rate changed when our concentration changed. Now, we've already determined that the concentration of nitrogen monoxide doubled between those two. So let's determine how our rate has changed. Well, in experiment 1, right here, our rate was 7.98 times 10 to the negative third. And in experiment 2, we can definitely see, or experiment 3, we can definitely see that the rate has increased. It's gone up to 32.0 times 10 to the negative third. Well, okay, so automatically we can see that NO is not a zero order reactant. If it was zero order, the rates between trials 1 and 3 would be the same. They're obviously not, so this is definitely not a zero order reactant. So how did the rate change? Well, it didn't double. This is way bigger than what double of this number would be. And so if I were to stick this in my calculator and divide these two numbers, I would find out that the rate quadrupled. The rate quadrupled when I doubled my concentration of this reactant. So which order tells us that when we double our concentration, our rate will quadruple? And the short answer is second order. So NO is a second order reactant. Now we already knew this because I used this example earlier, but now you can see the data and where I got that from, right? This is how you would solve for it if you didn't know that NO was second order. So now we need to solve for the rates of oxygen, because solving for one reactant is not going to give you a lot of information on the other reactants and how they're related to rate. So let's find two trials where the concentration of oxygen changes in some way, but the concentration of NO does not change, because we already know how NO affects the rate. Now we just want to know how oxygen affects the rate. We need a constant variable, right? So if I look between trials 1 and 2, I can see that the concentration of oxygen has doubled, but the concentration of nitrogen monoxide stayed the same. So that's good. That means that any change that happened to the rate between trials 1 and 2 is only to blame on oxygen. It's oxygen's fault if the rate has changed. So let's take a look. We know that oxygen's rate has doubled, but how has the rate changed, if at all? Well, we went from 7.98 times 10 to the negative third, and now it's 15.9 times 10 to the negative third. Now we know that this is not zero order because the rate did change, and it doubled. If you were to do this on your calculator, you would see that it doubled. So which order tells us that when concentration doubles, rate will double? That's first order. And so the overall rate law for this problem would look like this. And that's all the time